Things you should be comfortable with at this point. So kind of get you back into this chapter. Scatter plot. Bivariate data. Least squares regression line. Which is known as linear regression, which is known as the line of best fit. We also learned how to input this data into our calculator and graph the line from our calcs. The other thing that we talked about on Wednesday was the R value, and that is the Pearson correlation coefficient. I said there's three things that you need to know about the Pearson correlation coefficient, and that is tell me if the line's positive or negative. Then tell me if the relationship is strong, moderate, or weak. And then I told you end with linear relationship. Should be a sentence describing and interpreting that R value. You should definitely know that the range for R is from -1 to +1. The closest to -1 is great, and the closest to +1 is great. The closer you are to 0, the worse you are off you are. The other things, and we're going to cover it again today, you should be able to talk about the y-intercept in context and the slope in context. And sometimes that y-intercept means something in context, and sometimes it doesn't. The slope will always mean something in context because it's a ratio of change. It's a rate of change. Change in y over change in x. So it's the average based on that line of best fit. Remember that the least squares regression line is just a predictive model. It's not a guarantee. In fact, you saw how many of those stats plots or your scatter plots were not on that least squares regression line. It's that line of best fit. So that kind of summarizes where we were on Wednesday. We'll pick up from here. If you don't have index cards made on this stuff, I, again, encourage you to do it now because we're going to add more vocab today. And they're closely related, but they're not the same thing. All right. Linear relations, again, review. We've already got that, so I'm not going to go into that. Least squares regression line. Also already summarized that. Again, we use it as the line of best fit. That's what this is saying. This is really how we do it. I don't care about the calculations. I think in your notes it says calculate by hand. We're going to use our calculator, but I'm going to use easy numbers because we want to look at some other values, specifically these things called residuals. So this should be on the back side of the notes that I gave you guys on Wednesday. What we've got is just a simple data set. It looks like 4 pieces of data. What we've got is the number of years somebody's played soccer and then the number of goals scored that year. We're hoping to look at some linear relationship. And I think we'd stand before we go into this problem. Hopefully you think the more years that you played soccer, the more goals you're going to score. That would probably be a positive linear relationship, we'd think, but this is our data, so let's see what we got. Years played, so go ahead and plot your scatter plot. I think I put it there on the notes for you. Review, that's 1, 4, 2, 6, 5, 4, and 4, 2. Again, 4 data points. Make sure you're okay with that relationship. Years playing soccer, we're going to use the years playing soccer, that's our x value, and we're going to try to predict how many goals you'll score. I can't say that. Looking at the scatter plot, roughly speaking, what do you think? Positive linear relationship or negative linear relationship? Negative. Our line of best fit is probably going to split the difference between these data points, right? Okay. So, if you would, go ahead and put this data into your calculator, and let's run that least squares regression line. Again, part A in your notes says no calculator. I'm going to let us use calculator. Yep. What's that? Well, it looks like this. I mean, it's going down. Well, these dots, these two dots are higher than these two dots. So we're going to line that connects them. It's not going to go this way. That's this line. The distance between these data points and the line is greater than the distance between here. You want line of best fit is going to minimize the distance to the dots. So your line, if you were here, there's a big difference. There's a big difference between this dot and this dot and this dot. Right. So here, that's I think is. Edit. Looks like I got a bunch of junk in my lists. So clear your lists first if you haven't. Make sure your XYs line up. Let's clear that. We're going to run our linear regression. Hope you guys remember linear regression. That is stat, calc, and it's going to go down to number 8. Remember, number 4 puts it in algebra 2 in x plus b form. Stat's different. They put it in a plus bx. I believe it's number 8 here. Tell them where your lists are. List 1, list 2. Huh? I don't even know. It's exactly the same, and you're going to get the exact same linear regression with it. So technically, you can run it with 4, and just make sure you write it the right way. And I don't have any good reasons to lie to difference. All right. I'm sure there is one, but it's free. It's got to be arbitrary. Yeah. Does your data match mine? Yes. Okay. If your data matches mine, you should be okay with. And we're going to write it like this. Y with a little hat above it. Okay? Y with a little hat above it. This little hat above it means prediction again. Based on the data I have and my linear regression analysis, or my equation, I'm going to have 5.2 minus 0.4x. All right, I'm going to come back to that. Let me pause real quick. I'm going to do something real quick. And now you're going to run your linear regression again. Let's review. Make sure you can get your stat plot or your scatter plot up. Again, scatter plot is the dots. List 1 is your x values. List 2 is your y values. And before we do anything, our zoom stat, which is zoom 9. And you get your scatter plot right there. Scatter plot should look like mine. Remember, you as an individual, you can go and adjust that window. This is just what the calculator does. For me, I'm going to make my window 0 to 6, with my x scale being 1. It makes more sense. I don't like the decimals. My y, 0 to, I don't know, I'll make that 8. And I'll scale that by 1s also. That just helps me. When I do the zoom stat, it gets me in the ballpark of what my window should be. Now, if I need to sketch a graph on a test or on the AP exam, I'll go through and adjust my window so it's really easy for me to transpose it onto the exam. Does that make sense? Because you're really not going to put in your AP exam 1.36 for every, tick mark on your graph. So there you go. Now I've scaled it. You should already have something like that on your paper. Yes? Now, again, run your linear regression. You're going to press stat, calc, number 8. You're going to call it list 1 for x, list 2 for y. Now, this next part. Hit your comma again. I know you're going to do something unique. Press the bars button. Okay? Press the bar, list 1, comma, list 2, comma, and then you press the bars button. So your page looks like this. Go to y bars, that's y variables. The very first key is function. and you're going to make it toggle to y1. Here's what you've told your calculator to do right now. You've told your calculator to do a linear regression with list 1 being x, list 2 being y, and the output, the linear regression equation, that 5.2 minus 0.4x, you want to put it in the y equals. Okay, so now hit execute, or enter, sorry. You're going to get the same thing. We already talked about that. It's already been there, exact same information. Notice that our R value, again, do we agree that we have a weak negative linear relationship on our R value? Okay. Now go ahead and hit your graph. And now it should have your line of best fit drawn in there. By telling it to hit that y1, it's saying when you run linear regression, press your y equals, put the linear regression equation into your y1. So your output will represent all that output. Does that make sense? It's a nice little feature. Do you guys want to see that again for the calculator input?
Yes.
Okay, calculator input again. Stat, calc. 1 bar stat, linear regression, so that's number 8. Your x value, which is list 1, comma, your y value, which is list 2, comma, and this is the new thing. It's bars, y bars, function, and just have y1. So it'll look like that. Get in there, yeah.
Kind of clear what's the y1.
I think so, but I'm not. I'll just check it. What's that? So again, it'll put the line in there. You can always go put the line in by yourself. That's what we did last Wednesday. It's actually a little bit nicer than what I have up here because they've improved the programming language, so it prompts you. I mean, you guys are showing me it's x1. It says, where's your x values? You put list 1. Where's your y values? You put list 2. Then there's actually a thing that says store REQ EQ. That means store your regression equation. Where store regression equation is, that's where you put bars, y bars, and you have it say y1. That's the only difference in the inputs. All right, I think we're pretty good at that. And we've got that mapped. Calculate a line of best fit, we've done that. Graph the equation on a scatter plot. Label the centroid. This is a new piece of information, new vocabulary word here. The centroid. You may or may not see it show up. The centroid is actually used to calculate the linear regression equation. I haven't seen it recently on any of the exams. It is x bar, y bar, or the average of x and the average of y. Okay, the centroid in this case, looking back at your data, the average of the x values, you've got 1 plus 2 plus 5 plus 4, which is 12. 12 divided by 4 is 3. That's just the average. Remember, x bar is the average of x. And then y bar is the average of y. If you're looking at that simple data set, that would be 4 plus 6 plus 4 plus 2. That's 10 plus 6, which is 16. 16 divided by 4 is 4. So again, your centroid is the average of x and the average of y listed as a coordinate pair. So x bar, y bar. One thing I do want to point out to you is that the centroid will always be on the graph. I want to go to the graph. There we go. The centroid, 3, 4, will always be on your linear regression. It will always be on there. Okay? And that was under the trace function. Define, interpret the slope. This is big. This shows up almost every year. At some point, I can guarantee you there's going to be an interpretation of slope somewhere on the AP exam. Think about the slope formula. Slope, this is how I remember, change in y over change in x. In this problem, our slope was negative 0.4. Negative 0.4 over 1. I make anything a fraction, and then I put the y values up there. Let's see, y in this case is goal scored. And the x value is number of years played. I would write this, say, in the margin somewhere. This is not going to get you full credit for interpreting the slope. This is just how I remember it because I've been programmed changing y over changing x, slope, 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 slope. So make it a fraction and put the context. Then it's really easy to write the sentence from here. Okay? The sentence is going to be, for every year of soccer played, the number of goals scored will decrease by 0.4 per year. Does that make sense? Okay? For every 1 year of soccer played, the number of goals scored will decrease, it's negative, by 0.4 every year. Because, hey, in this case, we have a negative linear regression model. The slope is negative. According to this data in our linear regression equation, the more years you play soccer, the less goals you're going to score, which is also possible, right? This is just based on our data. Well, no data is bad.
Inaccurate.
Our slope is negative 0.4 from a plus bx. Remember? Our
Oh, yeah.
b is always going to be slope, and a is always going to be your y-intercept. What's that? The number of goals scored, because it's goals scored, your y-axis, number of goals scored will decrease by 0.4. No. Another context for slope here, and this should make sense to you guys. 0.4 as a fraction is 4 over 10, which reduces to 2 over 5. Another way to interpret this, our slope is negative 2/5. Another way to interpret it, negative 2/5. For every 5 years of soccer played, the number of goals will decrease by 2. Notice that that is another slope interpretation. Change in y over change in x. You will see slope both ways. You will see it as a decimal. You will see it as a fraction. Write it out the same way. Write the context in the context, and that will give you the ratio. In this case, negative 0.4, negative 2/5. Hey, that's the exact same thing. If you see the slope as a fraction, interpret it as a fraction. For every 5 years I play, I'll score 2 fewer goals. Or a player will score, on average, 2 fewer goals. You guys okay with that? Define A, as I told you, that is the y-intercept. This is, again, a predictive model. In this case, A is 5.2. So on this problem, an A value of 5.2 would mean, in this problem, the y-intercept has some meaning. If you've never played soccer, it is predicted that you would score approximately 5.2 goals.
Back in time, could you score more goals?
Yeah. Yeah, I'm going to talk about that right now. That's huge. Are we okay with that? All right, R value of negative 0.45, we've already talked about it. This is a weak negative linear relationship. That's all I need to say, weak negative linear relationship. Correlation coefficient, you're communicating how good or bad this line actually matches your data. In this case, it doesn't do a very good job. Now, here's our original scatter plot. All right? Roughly speaking, our line of best fit, I'm going to just sketch it in here. Our line of best fit was 5.2, something like this.
Has to go through 3, 4.
Has to go through 3, 4, almost does. Now it does. Okay.
Close.
So that's our line of best fit. Again, this is just sketch. You guys have it in your calcs. Some key pieces of information. What's up? Okay. Hopefully you'll agree with me that this line of best fit has been calculated on these 4 data points only. Our predictive model is based on those 4 data points. Right? I can't do anything else statistically besides the data that I have, and it's those 4 data points. Here's the big thing about linear regression. The linear regression model is only based on the range of your data. In other words, you really can only use it since you only have data from here to here. You can really only use it to predict anything in those boundaries. Anytime you make a prediction outside of those boundaries, in either direction, it's called extrapolation. And if you make a prediction outside of your boundaries of your data, you need to say something like this. I predict it to be blank. In other words, if I played soccer for 6 years, I predict I will score this many goals. However, it is outside of my data range, so therefore I'm in danger of extrapolation. That means I don't have any data to support it, but based on what has happened, if it continues to behave that way, this will be true. But I have no evidence to say that it will behave that way above or below it. So in the context of this problem, even my 5.2, that's extrapolation. My y-intercept is an extrapolation here. Does that make sense? To really carry it to extremes, in order to see that point of extrapolation, how many goals should you score, really, out if you played soccer for 12 years? Isn't this line going to keep going? It's a line, right? So if you extrapolate out to 12 years, which is up my graph, it should make sense to you that that y value, or the number of goals I should score, would be negative. So in other words, if this model continues to be true, at 12 years, I'll score like -2 goals. I'll score on my own team. Right? Probably not realistic. Roman said earlier, well, if this model keeps going up, then I can go back in time, and that's really what we want to do. If we go back in time, we're going to score a ton of goals. But again, that should not make sense in context. Do we see extrapolation and how it behaves here? Okay? Next part. Oh, we're not there yet. We hit the R value. Before I get to the residuals, I'll talk about that in just a sec. Find the number of goals scored when years played is 16. Okay? To make a prediction in linear regression, all you got to do is take your line of best fit, which in this case was 5.2 minus 0.4x. It's saying, what do you predict y to be when you play 16 years? Think back to Algebra 2 and Algebra 1. What does y equal when x is 16? 5.2 minus 0.4 times 16. And the definitely should come out negative. Negative 1.2. Okay? And I've already kind of covered this. Hey, it's predicted that if you play soccer for 16 years, on average, you're going to score 1.2 goals against your team. All right? Okay, so What? We've talked about R values. We've talked about line of best fit. The next thing that I want to talk about is a thing called a residual. Okay? And here's what a residual is. In this problem, we had 4 data points. Everybody agree with those 4 data points? They're in your calc. We had the 4 data points. Do we agree that as I move on that line, those are all predictions? We've talked about that, all predictions. Oh, stop. So I'm going to call it at 1. Roughly speaking, it's predicting that we're going to score 4.8 goals. Does that make sense? That's our prediction. We could find that out for sure if I want to. I'm just using my trace function because that's giving me my estimates on the line of best fit. But here's what we want to do. Another, say, measure of how good is this line, because that's the next thing that you're going to be asked to critically think. You notice your calculator does all this work for you. But I'm going to now say, here's a set of data. You've created this linear model. Is this linear model a good fit or a bad fit? If it's a good fit, you need to tell me why it's a good fit. If it's a bad fit, you need to tell me why it's a bad fit. Remember that BS part, be specific? I'm going to want to know why. Hey, you applied linear regression here. Great. Good or bad? Was it a good choice or a bad choice? Well, it was a great choice. Here's why. My R value is like 0.89. That's a great R value. I got a strong, positive linear relationship. Great. What else? I'm going to talk about those other things. R squared is going to be another thing of evidence, good fit or bad fit. Another piece of evidence right now is what we're talking about. Residuals. A residual is this. How far away is your actual data point? That's this thing right here. How far away is that actual data point to that predicted data point? How far away is your data point to its prediction? How close is your data on average to its prediction? How close is that to prediction? How close is that to prediction? Because in this case, this is my actual Y value there. Do we agree with that? And this right here that I have, that's my predicted Y value, isn't it? Y hat. Again, this is my actual Y value, and this is my predicted Y value. Well, wouldn't it be nice if we had something? Yes. The value of the distance or the gap between your actual and the predicted is called a residual. That's what a residual is. The difference between your actual data piece and predicted. So as a definition for a residual, calculate the residuals. Residual, I'm going to write it as actual data minus the predicted data. Again, Y hat is predicted. In this case, we will have 4 residual values. Why? We had how many data points? 4. If we have a data set of 20, we will have 20 residuals. We have a data set of 100, we will have 100 residuals. You can only have the same number of residuals as you do actual data pieces. So let's calculate the residuals real quick. It's always actual minus predicted. So we can do that a couple of ways. If you would like, you can do it by hand in this case, because we only have 4 data pieces. We can do it by hand. But let's see if this idea doesn't make sense. In list 3, I'm going to have list 3 equal to my prediction, which is 5.2 minus 0.4. And I would put x there, but what am I really going to put? Do we agree list 1 there? Isn't that where our x values are? And so if I put 5.2 minus 0.4 times, I'm just going to go like this. I'm going to go parentheses 0.4 times list 1. Doesn't it say 5.2 minus 0.4 of x? And now over in list 3, once I enter that, isn't that now my predictions? Do we agree with that? Any questions on what I've done there? Yo. List 3 equals. You make sure it's toggled up there at list 3, not in the column. And we're going to tell it to equal 5.2 minus 0.4 times, and then list 1 is just second, and then the number 1, because that's where list 1 is. Close that parenthesis and hit enter, and that gets your predicted. So do you guys agree? In list 2, I have my actual data. In list 3, I have my prediction. Is that right? Is everybody okay? Thumbs up. We're okay with this? Okay. So if I want to get my residuals, isn't a residual actual data minus predicted data? Do we agree with that? So can I tell list 4 to equal actual minus predicted? Sure. That's just going to be list 2 minus list 3. Now I have our residuals there. I can make what's called a residual plot. Okay? So I'm going to do that right now. Do you agree with me? And here's the idea. A negative residual here. My 4 actual data pieces. A residual of negative 0.8, a residual of 1.6, a residual of 0.8, and a residual of negative 1.6. Critical thinking here. If my residual is negative, my line of best fit over-predicted my actual data. I'll say it again. This negative residual, negative 0.8, actually over-predicted what my actual data said. In reality, I scored 4 goals. My predictive model said I should have scored 4.8. It should make sense to you. Sometimes the line of best fit will over-predict. Sometimes the line of best fit will under-predict. Hey, I have a positive residual, 1.6. I actually scored 6 goals, but my line said I should have only scored 4.2 or 4.4. Does that make sense? Same thing for 0.8. I actually scored 4. It predicted 3.2. I under-predicted a little bit. I actually scored 2. It said I should have scored 3.6. It over-predicted 1.6 goals. Residual, actual minus predicted. Negative value means the line of best fit over-predicted. Positive value, the line of best fit under-predicted. Next thing we're going to do. It said calculate residuals. We've already done that in our calculator. Do you agree our residuals are sitting in there in the calculators? All right. We can create a residual plot. A plot of the residuals. Our residuals are sitting in list 4, aren't they? Does everybody agree with that? Okay. So exit out. Clear out your y equals. We don't want that line of best fit in there anymore. And now go up to your stat plot. I want to plot my residuals. I want to plot my residuals. Okay. That means for your x, you can really have, in this case on a residual plot, your x-axis can change, and I'll show you in just a second. Right now, we're going to keep it at list 1. We want our y in this case, our y-axis, our vertical axis, to be our residuals. Where are our residuals? What list are they sitting in?
4.
List 4, perfect. So now it's going to have my x values, which is my same original x values, but instead of the predictions in the scatter plot and line of best fit, It's only going to show me the residual plot. So we're going to go ahead and exit out of that. Make sure you re-zoom stat that, because you're going to have different boundaries. Right? Zoom stat, zoom 9 after you've got that set. And again, you can rescale your window. I would. 0. My max X value, 6. My scale, I'll keep that at 1. Looks like my Y values go from -2 to +2. I'll make that -3 to +3 and keep that at a scale of 1. Just makes it easier for me if I have to transpose it onto a piece of paper. Yes, that scatter plot looks similar to the scatter plot we had before, but this is a residual plot. If you hit your trace, notice right here, 1, -0.8. When x equals 1, you have a residual value of -0.8. When x equals 2, you have a residual of +1.6. When x equals 5, you had a residual value of 0.8. And when x equals 4, you had a residual of -1.6. Okay? Now, residuals down here. Did your line of best fit over or under predict? Over predicted. So negatives is over prediction. Positive residuals, under prediction. And that should make sense. Okay? Things you're looking for. Things you're looking for in your residual plot, and I'll talk about this in a little bit. You look for patterns. Okay? Patterns. A good residual plot has just as much above as it does below, and it doesn't look like anything specific. Here's the patterns you're looking for in a residual plot. Because you can have a lot of different residual plots. Don't want that. I could have a residual plot for a given set of data that looked like something like that. That's a clear shape, almost a parabola. It consistently overpredicted, underpredicted, overpredicted, and underpredicted. That's a pattern. Patterns and residuals are not good. So look for patterns. Here's all you need to say. Remember, I'm talking about evidence and being specific. You should be able to be specific about your R value. Next, you should be able to be specific about your residual plot. You need to say, hey, there doesn't appear to be any patterns. If there's no patterns, then the linear model is the best fit. Notice when we were in your calculator, there was quadratic regression, there was cubic regression, there's quartic regression. Those are all different models that you can do with your data. Remember, quadratic is a parabola. You can try to model it after a parabola. Quartic is square root. Those things are all models that you can use. We don't do it. The only thing that we do in this class is linear regression. If there's no patterns in the residual plot, you say the linear model is the best fit. If there's patterns, then you need to say a non-linear model would be better. And you don't have to say what nonlinear model would be better. That's in a different stats class. In this class, you just need to be able to say, yeah, yeah, this linear model is a good fit, or no, there's a pattern in my residual plot. I think a nonlinear model would be better. Okay? And you're going to look in your homework tonight, there's going to be some patterns, or it's not. It's don't be like Sherlock Holmes and trying to be like, I think there's a pattern here. AP stats, and for the purpose of this class, it'll be pretty evident if they want you to say a nonlinear model is going to be better. Something like this, for a residual plot, that's a pattern. Okay? Something that looks like a parabola, that's a pattern. Something that looks like okay. Something that looks like you took a thing of spray paint, you know what I'm saying, and just dripped it off, something like that. That's a good residual plot. It needs to look messy. A good residual plot is messy. And think about it. A messy residual plot means it's consistently over and under predicting. It's consistently over and under predicting. It's never perfect, but on anywhere, any given point, you might overpredict, you might underpredict. When there's a pattern, I can tell you. When there's a pattern, I can say, well, from 0 to 2.5, it's going to what? Over or underpredict? Underpredict. From 2.5 to 7, it will consistently do what? Overpredict. And then from 7 to 10, it will consistently, right? That's a discernible pattern. A nonlinear model is better. Okay? All right. What else do we got on this? I don't want that one. I don't want this. No. That. Okay, we did that already. Let's see. Do I have a checkpoint on there for you? Okay, let's go ahead and finish it up. I want you guys to do this one in your calculator, please. You've got corrosion. The steel frame is the most important factor affecting durability of reinforced concrete buildings. The depth of the corrosion, I'm going to make that X. And Y value is going to be the strength. Think about this in terms of real structure analysis. I can measure how deep a piece of steel is corroded. That means rusted out. If I know how deep it's rusted out with a meter stick or a centimeter or a millimeter, I can tell you how strong that piece of steel is. I can also predict if that model is going to collapse in an earthquake. Valuable in the Bay Area, yes. Salt air means things rust. So I want you guys in your calcs, give me the line of best fit, give me the scatter plot, and show me the scatter plot with the equation graph. So I just want to see that in your calc. Done already? Yeah. Bless you. Which is good. You got the scatter plot, you got the equation, least squares regression line. At this point, you should be able to interpret the R value. R value on this one was pretty good. Is that right? Yeah, because you said it was good, it's going to be good. How about negative 0.968? That's what I got for R value. It's a strong negative linear relationship. It's a strong R value. That's good. So this suggests this is a good linear model. Next thing that we need to talk about. Is it a good linear model? Well, you should have seen when you did your graph, hey, that line is really close to a lot of our data points. The scatter plot matches our line of best fit. A linear model is good. The next piece of information we want to be specific is a residual plot. So, let me show you a magic. There's some wood magic here. Rerun your stats. So hit stat calc. And this is just putting refreshing the information. It's probably still there. For us, it's what, 8? List 1, comma, list 2, comma, and the lines, you guys are there. And we've got it run. Okay, that's the old problem. You guys have a different one. Your R value should be negative 0.9 something. Right? Okay, I'm going to show you how to do a residual plot really quickly, because remember I modeled list 3 and list 4, and some of you guys already got a residual plot on that. Okay? So you guys are ahead of the game. Let me show you something. You guys have the information. This information is now sitting in temporary memory of your calculator. So go up to your stat plot. And now, in your stat plot, you still want it to be a scatter plot. We want to do a residual plot now, right? So keep your calculator looking at X list is list 1. Now on your Y list, in the past, remember I calculated the residuals by hand. I put them in list 4. Wouldn't it be nice if the calculator was smart enough to calculate the residuals for me? That would be great. It almost like it already does that. So what I want you to do now at your Y list, make sure you're targeted there, press second stat, which is going to the lists. There's a name of some lists there. Scroll down to the bottom list, you should see something that you really like. It says resid. That must be short for residuals, and indeed it is. So, your X list is list 1. Your Y list is now your residuals. Have the marks be whatever you want the marks to be. We will need to exit out. Personally, I'm going to clear my line of best fit. I don't want my line of best fit going through the middle of my residual plot. That will make it look messy, yes. To go back to how I got the residuals. We are at our scatter plot. We're targeted to the Y list. To get to the residuals, it will say second stat. It'll bring up the names of the lists. I believe one of the very bottom ones is resid, number 8. Hit enter, and that'll put the residual in there. Okay? I took out my Y equals. At this point, you will want to zoom stat it because remember your window is set for your linear regression model. Zoom stat. That'll now get your regression, your residual model. My residual model should look different from yours. This is from the soccer, the 4 data pieces. Mine's going to look different. Compare your residual plot to the people around you and see if it matches up. Now, eyes, ears, real quick. If your residual plot does not match up your neighbors 100%, but they're close to the same, my guess is your windows don't say the same thing. So why doesn't everybody adjust their windows to the same scale? Okay? And I have no idea what scale you guys want to adjust it to. What's your range for your X values? You guys, it's from 0 to like, your X values go all the way up to 65, right? 70? I don't know how high they go. 0 to 70 for you guys? Scale by 5s. I think the residuals, I don't even know how long they go. Probably -3 to +3 would be good enough. Scale by 1s. Okay? Now compare your residual plots again and see if they match. And they should.
I can't get mine to work. When I do second stat, I only get one number.
The residual for X equals 8, 0.52, sounds good. You can find that by just highlighting it. If you have your residual plot up, you can hit the trace function and go to where X equals 8. Again, I have the soccer data up. You can just trace over to X equals 8. 0.49? 0.4986. Okay. So I'm guessing something's not right there. Okay. Next thing. Predict depth of 90. Predict depth of 90. You have a linear regression model. You can, 2 things. You can plug it in and substitute directly and use your calculator PEMDAS and get that prediction model. The other thing you can do, in your calculator, there's a very nice thing. Under the trace function, second calc. If you hit value, you want to calculate the value. You want to calculate the value when X equals, I can't do it on this one, let me get the right, because this is a residual plot. Do you guys, let's go back to, Are you guys okay with me to go back to your linear regression to get it up? Okay. Why don't I hold that for tomorrow? Because I think we're running short on time. So I'll show you how to calculate the value tomorrow in your calculator. For today and tonight's purposes on your homework, if it says to calculate or predict, just plug it into the predictive model and hand substitute. Is that okay? And I'll show you the trick on the calc tomorrow. And I think we've covered everything that's on this one. Linear regression equation. I kind of killed two birds with one stone here. Good fit, find and interpret R. Residual plots. Tomorrow we will hit standard deviation of the residuals. Tomorrow we will hit standard deviation of the residuals. And tomorrow we will hit R squared, coefficient of determination. Okay? That's where we'll pick up for tomorrow. What time are you guys out? 14, okay. So we'll hit coefficient of determination, and that's tomorrow. And that should be it. Yep. At this point, assessing fit of line. I said, hey, be specific. These are the 4 things you're going to want to know. Does the scatter plot appear to match with your with a line? Yes or no? Is the residual plot, does it have a pattern? Does it not have a pattern in it? The R value. How is that R value? And tomorrow we're going to talk about R squared, and tomorrow we're going to talk about standard error, which is a standard deviation of the residuals. Okay? And that's about it for linear regression. It's nice. It's easy. Hopefully you guys are getting the idea around it's not the calculator's doing the work, and it's about us understanding what the calculator's doing for us. Okay? All right. Homework for tonight. It's going to be the second part and a little bit more. Yeah. Oops. Okay. There's your homework assignment. Tomorrow. Yep, both of those. So I'll be checking actually 3 sets of homework tomorrow. First 5 minutes of class, I'll be checking 3. That'll be the previous one from Wednesday of last week, and then tonight. Okay? The other thing that I'm going to pass out to you, I'm going to ask you to read tonight. We will discuss tomorrow. This is going to be your linear regression project. So read it tonight. We will discuss tomorrow. You guys play games? You guys should have been well. Done pretty well. What? You guys didn't play good or were they good?
No.
Yeah. Did you get a lot of play? Well, that's okay. Then you get a lot of play. Who do you guys play?
One is definitely lighter than the other.
You guys get stomped by Rio B?
Well, they didn't have runs.
Did you? Good.
Unless I wanted to eat.
Yeah, you should have beat that. You guys probably ran Rio Olympic before. Yeah. So Rio Olympic close. Rio B ran close? Okay. That's good. That's probably a good game. That's probably. And you guys, you stomped for it. Cross the play. Oh, Castle Roble? How'd you guys do against him? They tend to be up and down, so.
Yeah, they do this, but not that much.
All right, this is your project. A quick clarification. It is going to be a group. You can do it as a group. You can do it as individual. I won't allow more than 3 people working together. So 3 people is the max in a group. The other thing that I'll just talk about briefly is that you will be generating data on it. I think it's 16 data points, another 16 coordinates per person in your group. So if you do it alone, you only need 16 pieces of data. If you do it with 3 people, you're going to need 48 pieces of data. Does that make sense? Okay. You can think about it, read it over. You can start thinking about topics. Like I said, we will talk about this quite a bit tomorrow, and I'll let you know what I expect from that. We clear? Okay.
This is a test for the Thursday.